Hey, we made it to chapter 20. It's our last chapter to discuss. Give yourselves a round of applause. I'll wait here. Okay. So chapter 20 deals with nuclear chemistry and nuclear reactions and a few associated things along with it. By the time we're done, we'll get into some kinetics of nuclear reactions and things like that. But what I expect everybody to do is to download the guide sheet that is there in Blackboard. There's a 4-page guide sheet for the introduction to fundamental nuclear processes. And so this sheet I usually go with students in class with it. We kind of go through everything and write in all the example equations and things that you'll see in here. We're still going to kind of do that as a group here, and then we'll get into some of the other things. So this first video is about just an introduction to nuclear chemistry, and it is pretty bare bones. We don't get really deep into a lot of nuclear things. We talk about the basic reactions and then kinetics and a few other things. But the term radioactivity came about a little before 1900 as people were looking at materials that had these strange properties. And they didn't understand these properties, but they were kind of just playing around with things. And one of the things that they were playing around with were classes of rocks that were capable of exposing photographic plates. So if you think about photography in the late 1800s, it was those large tripod cameras with the hood that you went under and somebody standing there with a magnesium flash to go off at the right time. And they actually reached around and pulled the shutter away and put it back on, and that was taking the picture. And the picture was put or assigned on this glass plate that had been chemically treated. And then they retreated the plate to develop the picture. So these glass plates were like film. I know a lot of you don't know what film is either because most of you have grown up during the digital camera age. But this plate, when they developed it, they got the picture. And so the plates that they bought came individually wrapped in heavy black felt paper to keep light out, because that's the point, right? You got to not expose them until the right instant. And so they came wrapped in this light, tight packaging. And what they discovered was, and this came about because of these kind of just playing around with these rocks, is that if they took a plate and took it out like they were going to put it in the camera, but maybe they set it on a bench top and they put these rocks that had these strange properties on them and took the rocks off and developed the plate, it had a picture of the rocks on them, which was really bizarre for anything that any of them had ever seen in the past. It was something that would expose these plates without any light, okay? And the story goes, and I don't know because I wasn't there, it was over 120 years ago, but the story goes that William Röntgen was one of these guys that was working on this kind of strange property of these rocks. And someone brought in something to him to his desk, and to clear off space on the desk, he opened a drawer that happened to have some of those wrapped, unexposed photographic plates in it, and just scooped the stuff off his desk into the drawer so he had a space to work. Some of the things that he scooped off into the drawer were some of those rocks. Probably didn't worry about it because all the plates were wrapped. But when he later developed those plates, the pictures of the rocks that he scraped off his desk into the drawer were on them, even though the plates had never been unwrapped. So this was a completely new characteristic of this light, or whatever it was at the time that they were wondering what it was, that it could go through paper, something that could go through materials. The first time they'd ever experienced anything that could be verified to go through a material. So it completely revolutionized the thought process for what was going on with these rocks. Now we had this strange radiation that they called X-rays because they didn't have a better word for it. And they started to look at those, and in doing so, they discovered several other nuclear processes that went along with it. So they were coined as X-rays, and Röntgen refused to patent them because he thought they were something that belonged to everybody, not just something that he should profit off of, which is pretty amazing. Can you imagine how much X-rays would cost nowadays if we had to pay for patent rights also for those things? So immediately, scientists all over the world started jumping on this. Let's discover what they are. Let's figure out what they are. Let's characterize and come up with all the properties and all that kind of stuff. One of those folks was Marie Curie. Marie Curie in 1898 coined the term radioactivity, or thereabouts, 1898, discovered polonium, discovered radium, also died of cancer. A few years later, a couple years later anyway, Rutherford came along and confirmed at least 2 different types of radiation, other than just these X-rays or something else. Alpha particles and beta particles. Shortly thereafter, gamma rays were also discovered as existing. Okay? So I'm just going through this same handout that you guys have. So the figure in the handout does get a little bit small. So we're going to look at that. Grab a new marker here. So one of the things that they did was they took this radiation that they were characterizing and they fed it through an electric field. You've heard me say this before. Scientists at one point were all about electric fields and let's push all this stuff through the field and see what it does. And this is one of those things. So they took one of these radioactive sources and they put it inside a lead box. And that lead box had a pinhole in one side. And what it did was it allowed them to essentially point the radiation. Kind of like a flashlight, but it's not a flashlight. But radiation coming out the pinhole was going in one particular direction. And so they took that radiation and they had it pass between 2 electrical plates. Like poles of a battery. So these 2 electric plates, the potential difference between them forced the particles that were going through to split and change direction. So some of these particles deviated upwards, some of them deviated downwards, and some of them went straight through. And they had a detector over here that would flash when particles hit them. So they saw flashes here, and flashes there. Well, if these particles or rays or whatever they think they were at that time went through this plate separation, the things that deviated upward toward the positive plate must be positively charged. Because opposites attract, right? Things that are negative are attracted to things that are positive. The things that deviated toward the positive side must be negatively charged. Opposites attract. The things that did not deviate, the things that went straight through, must therefore have no charge. And so they discovered that there were multiple types of radiations coming out of this material. And as they characterized them, they did quite a bit of geometry, quite a bit of physics, and they determined that the positively charged particle had a mass of 4 and a nuclear charge of 2. So now we're writing isotopic symbols from way back last semester, right? A mass of 4 and a charge of 2, and they called that an alpha particle, alpha for alpha particle. Well, if you think about it, things that have a mass of 4 and a charge of 2, those are helium nuclei. Mass of 4, a nuclear charge of 2. So you will see alpha particles written as 4/2 helium. Now before we go too far here, when we look at symbols like this, nuclear physicists and scientists care very little about electrons because it's all about nuclear processes. Things are happening inside the nucleus. So we don't see any charges listed on these sorts of symbols normally. The things that were deviated toward the positive plate, which meant they were negatively charged, after the same kinds of geometry and physics calculations and all those kinds of good things that we're not going to do, they discovered that there was essentially no mass and a charge of -1. Now we do see charges on the little numbers here, but not overall as an ion charge. So something that has no mass and a charge of -1, well, they called that a beta particle but it's also identical to an electron. Because something with no mass and a charge of -1, that's an electron. We've been dealing with that the whole year, right? So you'll see these both listed as alphas and betas with their appropriate masses and charges, or as heliums and electrons. They both mean the same thing. Okay, now for this particle that went straight through without being altered in its course, that had no mass and no charge. No mass and no charge. Well, we'll call it a gamma because we need a letter for it, alpha, beta, and gamma. But what it really is just a photon of light. And our old abbreviation for a photon of light was h nu. H was Planck's constant, nu is the frequency. That's the formula for the energy. It just transfers of energy. So gamma rays, not particles, alpha particles, beta particles, gamma rays. Gamma rays are nothing more than light being given off by a highly excited isotope nucleus. So gamma rays are among the highest energy photons of light that we encounter. Cosmic rays are the highest. Then the next step down in energy is gamma rays. Okay? Huge amount of energy being carried by these. And what turns out happening is that a lot of the particles that go through these fundamental processes like alpha and beta and a couple others that we're going to get to, the products of those are highly excited. And so instead of being at ground state, they are way up here. And when they return to ground state, they emit a photon of light that has a huge energy. And those are gamma rays. So it's not uncommon for us to see an alpha emission that also has a gamma emission along with it, or immediately after. But it does not change anything about the makeup. Alpha emissions and beta emissions change or transmutate the element from one into another, but gammas do not because there's no change in mass or charge. Okay? So these are the three initial fundamental nuclear processes. Okay? Now when we come back on our next video, we're going to also look at positron emission. And that is when we release 0/+1 beta, a positron, a positively charged electron. It's like an electron, but has the opposite charge of the normal one. And we're also going to look at electron capture. And its process works differently than the others. But these are the 5 fundamental processes: alpha and beta emission, gamma emission, positron emission, and electron capture. So we come back, we're going to look at the rest of the pages of this handout, and we're going to go through and do those examples. Okay? Be right back.